Okay. So hello everyone, this is Luboš Pirkl from CFD Support, and welcome to the webinar about the new benchmark we did here at CFD Support. We call it BIMBOL FSI benchmark, and it will be our pleasure to show it to you today, especially in how it works in our new simulation environment, which is called TCAE. So I hope all the techniques work well. In case of any technical problems, it happens all the time. So in case of any technical problems, feel free to contact us in the future and we will gladly answer all your questions and comments. This webinar is being recorded. By the way, give me a second. Is it recording, Radek? Well.
Yeah, it is recording.
Yes,
so
it's recording. Okay, thanks. Okay, so the webinar is really being recorded, and its recording will be made publicly available. So yeah, I think it's time to get to the action. So I will introduce the webinar speakers. This is me. My name is Luboš Pirkl, and my current job at CFD Support is telling the world about what we do and what's going on. And today I am here with my colleague Radek Máca, who is our head engineer and senior developer. And let's check him out. So Radek, knock knock, are you there?
Yes, sure, I'm here.
Oh, okay. Yeah, right.
Dramatic pause, right?
Yeah. I get it. Yeah. So I hope everybody else get it. So Radek, how are you?
Yeah, I have in an amazing mood, so I'm good.
Okay. Yeah.
Thank you.
So okay, let's see if the webinar will be amazing too. And let's go ahead. So here's the agenda. There will be in the first part there will be a quick webinar introduction. I will give a general info about mostly about the company and TCFD or TCAE now, and yeah. So I will give the introduction. After that, Radek will show the real work of the BIMBOL FSI benchmark, how it's set, and what are the results, and what we did. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. I think there is a window in the GoToWebinar menu. So feel free to ask your questions anytime during the webinar. All the questions will be answered. Some of them will be answered right away in the webinar, and all the rest questions will be answered later via email. So feel free to ask your questions. Your feedback is very important to us. So yeah, ask whatever you want. It's your time, so use it to the fullest. Okay, so I'll start with the introduction. So CFD Support is the name of our company. The company was founded in 2009 as a technological startup, and we are located in Prague, Czech Republic, and our main business is CAE analysis, simulations, specifically CFD, FEA, and FSI. All these simulations and analysis. Yeah. So we have very good team. We have very powerful team of smart alpha males who really know what to do, and we are developing software and doing all the stuff around. So our main business is developing software, which is called TCAE. It's a comprehensive simulation environment, and yeah. So that's what our webinar will be about. Yeah, we have recently released the latest new version, TCAE 2009, which was really a big shift in what we do, because it's new and there are many new stuff in it. I guess you know it, but still TCAE is based on open source. We love open source. It consists of 46 open source packages, and a lot of time and effort has been spent on developing those packages by the open source community, and on top of that we have spent more than 30 many years of specific development to make it available for in the graphical interface and make it robust and make it usable, and to really prove it works. And so a lot of work has been spent, and TCAE is now comprehensive simulation environment. It consists of software modules. So there are specific software modules which are in fact standalone software pieces. So they can work either together in a connected workflow, or they can work just like standalone tools inside other workflows. So it's very flexible and very much variable in terms of its use. So TCAE has a strong integration ability. It was developed from the beginning in a way to fit any existing workflow which exists already. So it can replace, for example, just the CFD part, or it can do just meshing, or both of them, and it can be used in a combination of all the possible software pieces available in the market, either open source, either commercial codes, either in-house codes. It's TCAE is always here to be used inside existing workflows. Okay, there are there are lots of stuff. I'm not gonna go into too much into details. I'll go ahead in here. It's very important that TCAE has a graphical interface, which is where the user can set everything from scratch, and run the simulation in it, run everything, evaluate the results, and save them and get back anytime. So it's very comprehensive in these terms. TCAE is unlimited, so there is no limitation on the number of users. There is no limitation on the number of jobs or cores. There is no limitations on hardware installations. So its users can use it to the fullest in terms of its users and hardware and everything. So this is a big thing in terms of business model. TCAE is definitely very accurate. We are clearly focused on the accuracy. I would say we are obsessed with accuracy. TCAE is always aimed on particular applications and particular simulations. So it's not software for everything or for anything. It's software aimed especially on turbo machinery simulations like pumps, compressors, turbines, and fans and all the stuff, and also for the external aerodynamics, the external aerodynamics. Yep. So it's definitely not a general purpose code. It's a specialized code for special applications. Accuracy is our big goal, so we do a lot of tests, a lot of sensitivity tests and everything. So we are ready to prove it's accurate. And we especially believe that any successful project in CAE and in simulation is a matter of skills, experience, patience, and dedication, and it's definitely not luck or quick actions. So it's needs to be resolved to a particular quality. We do quite a lot of benchmarks, so we always measure how accurate we are, and we are ready to show it. So accuracy is our very high priority. TCAE is automated. It's extremely effective because it's automated. Its users can use it in a simple way. They can just put the data in, let the TCAE do the simulation, and just pull the data out. So they can use it as a black box, or its users can use it as a highly sophisticated simulation code where all the options are open, even the source code of these open source tools is open. So it's extremely flexible, and the beauty of it is it's the user who decides how deep to dive into CFD or CAE or FSI, or not at all. So it's the user who decides how much to deal with the details. That's the beauty of it. We deeply believe in the importance of technical support. The technical support is coded in our company DNA, or after all, it's coded in the name of the company. So we believe technical support is extremely important, and yeah, so we are kind of proud of our technical support. We use a special system, OS ticket, for treating the technical support. It's unlimited, it's very flexible, and we have custom approach to every customer, and no one is ever left behind. We are like a family, and with our clients, and also we our colleagues here. So I would say our company is one-way ticket. We have never lost a customer to a competitor. Once someone starts collaborating with us, he stays. Okay, I'll continue. Our software is especially developed for Windows and Linux. We have two branches, which are the workflow is exactly the same, native compilations, and also the remote desktop into the graphical interface is possible, and also the batch mode is possible. So it's very powerful in these terms. Yeah, the meshes are either the meshing system is either automated, so the TCAE is ready for automated meshing either on the CFD side or FSI, I mean TFEA side, and also the external meshes can be loaded into the system. So it's always up to the user. We always leave the decision about the mesh up to the user. Some users prefer automated meshing, some users prefer their own meshes because for historical reasons or for some specific know-how. So we always leave the meshing decision up to the user. That's quite important. TCAE has a very, I would say, robust and very detailed post-processing system. Every simulation, either CFD or FEA, has its own HTML or PDF report. So anything which is run is also evaluated in an automated system. The visual results can be post-processed in the ParaView. ParaView is extremely powerful post-processing tool. And also all the integral results are written down into the tabulated CSV files. We have implemented a special post-processing tools like meridional average or blade-to-blade view directly into the ParaView. So there's turbo post-processing, and all the reports are available in the HTML and PDF automatically, which is very useful. And I would say, maybe if I should say one thing, maybe this post-processing tools and the reporting system is I would say it's one of the best what we offer. Okay. TCA is continually developed. It's always developed. We every day we write down new items on our to-do list, and also we finish some older items. So it's continually developed. We gather the requirements from our users, and we create like pools of them, and then we put them into the new version releases. Yeah, and the development is definitely open-ended. What I know for sure, and we will always keep developing, because we always it's our passion. We always innovate. We will always keep adding new features and new plugins. We call it the horizontal development, where we are adding new simulation plugins, new simulation tools, and we are adding the complexity and multi-physics. And in the vertical development, we are adding new applications, new capabilities, and high-tech methods inside those verticals. And I can promise we will keep developing, because we believe in innovation, and we believe that there is a lot of stuff that can be still implemented and move all the business and all the field upwards. Okay, there are a lot of application examples. I'll be reasonably quick here. TCAE, its former software name was TCFD, has always been best on turbo machinery simulations, so like pumps or fans or hydro turbines, compressors and turbochargers and wind turbines. And later, what had worked so well in turbo machinery field, we have extended to external aerodynamics like car bodies or aircraft, or for valves and hydraulic valves and various manifolds, exhausts manifolds, intake manifolds, and also combination of turbo machinery and external aerodynamics like propellers and ship hydrodynamics, and also drone propellers and building wind load and heat and comfort. We've always put a lot of accent on benchmarking, so we did a lot of benchmarks for almost for all of our clients. Of course, there's always a problem with the confidentiality of the data, so some data we were allowed to make available. So there are a couple of benchmarks we did. Again, I'll be reasonably quick here. We did this Potsdam propeller and Francis turbine, for example, and centrifugal fan and compressor and parallel scaling study, and also the aircraft, etc., etc. We did a couple of optimization studies and very advanced meshing systems, and this is today's case. I'll stop here for a while. This is what's on the table, what we did, because the TCAE is quite new software. We decided to create a benchmark, which is FSI benchmark. There's involved the fluid flow, so we have created such a case, which is, we call it BIMBOL, because there's a beam and the sphere at its end, and this beam ball is exposed to the airflow which is flowing on it, and yeah, and obviously the forces acting on the sphere are acting at the beam, and we can run this in the TCAE, run a complete simulation of this. And the beauty of this BIMBOL benchmark is that the analytical solution can be evaluated analytically. So we know what are the results. We can write it down on the paper. The analysis has been done and publicly, and it's on our website and also in the PDF. So it's completely available. You can go there and look for it and download it and look if we did it correctly. We will be very much interested in your feedback. So feel free to give us feedback on this study. And yeah, so the beauty of it, so there's analytical solution, there's the simulation of CFD, then FSI happens, and the forces from CFD are like prescribed as the input as the loading for the FEA analysis, which tells us for example the beam deformation, this delta, how it's deformed at its end, and for example maximal stress, which is typically here below at its the fixed end of the beam. And yeah, we did the comparisons, we did the simulation and the analytical solution, and guess what? It fits very well. I think it's amazing, Radek, right? And yeah, that's what it is. And now I think it's time to hand over the presentation to Radek. So let's check him out. Radek, are you still alive?
Hello, Luboš. Yes, I'm still alive.
Great,
So
great,
I
great.
will,
This COVID situation is pretty serious, right? In Czech Republic. So I
yeah,
always
definitely.
ask when I because I can see you. Okay, so you
So,
should share your screen. Okay, okay.
mhm.
So
Can you see my
it's the
screen?
stage is yours. Yes, we can see it. Stage is
Okay,
yours.
great.
Go ahead.
Okay, thank you, Luboš, for your amazing introduction and first part of the presentation. And now I'm going to the second part of this training, or not training, of this webinar, which will be kind of a little bit training, because I will show you how to set up this particular case of the ball beam benchmark from very beginning. So to do so, I will simply open the TCAE software. So this is how it looks in the graphical user interface. As Luboš already mentioned, the graphical user interface is implemented in ParaView, which is an amazing tool for visualization of the data. So we have incorporated into this tool, and you have many options how to set up simulation, process the simulation, and post-process the simulation. So you can use both TCAE features and also the ParaView features. So everything you can done within one graphical user interface. Okay, so at the beginning, what we will need to do is to create a computational mesh. So for now I will switch off the TCFD and TFEA module, because I will be playing just with the T-mesh, just with the meshing. And then when we will have the mesh ready for the simulation, then we will set up the simulation. So these buttons stands for enabling and disabling each module, TCFD or TFEA. So I will switch them off, and I will be playing just with the meshing. So just shortly about the layout, the important part is the pipeline browser, in which you can see several items which holds the input geometry or the meshing geometry. It holds also the setup parameters of each module and so on. So anytime you click any item, the new properties and new parameters will appear in this part of the graphic user interface. Then there is the render view for the visualization. There are many other views which we will see during my part, and here are some log window to see what is happening, and so. So let me start. So first of all, here we have a window in which we can create and store everything what we set. So we can create a setup file, TCAE setup file. So I will navigate into our working directory for today. So within the installation of TCAE, which is usually installed, or the default place is on the C drive, TCAE, the version of TCAE, and here are the tutorials, some four basic tutorials for the test purposes, which are delivered within the TCAE installation. And today's case is this BIMBOL FSI benchmark. I have already something simulated, but what you will see here is the preset configuration file, always with the TCAE at the end of the file, and the STLs, so the input geometry. Okay, so I will create a new case. So my setup, for example, and in this file I will be storing everything what I will set. And anytime you can reopen the project and continue, or just run the simulation if everything is preset. Okay, so then we will start with the meshing part. So in the T-mesh, we can create the mesh for finite element analysis and for CFD, for both of them. So because we will do both of them, so I will check that I would like to create the mesh for both for CFD and finite element analysis. Okay, then we have two menus for CFD mesh and FAI mesh. So I will start with the CFD mesh. So there are several menus. Here are some rotational reference frames which are applicable for turbo machinery cases. So this is not the turbo machinery case, so I don't need to bother with this menu. The components is the most important part because here we load the both the external mesh if it's ready, which is not this case, or the input geometry. And the input geometry has to be exported from any cat-like software in the STL format. So because we are going to do the ball, so we are yeah, the ball, the external aerodynamics of the ball, so we have to create some virtual tunnel geometry, which we can do it implicitly by this check at bounding box for external flow. So if I check it, then some virtual tunnel will appear in my render view. So this is very helpful for this virtual tunnel-like simulation. The turbo machinery case is not this case because it just enables additional options in the meshing which are tailored just for the turbo machinery cases. So I will uncheck this option. Scale factor just tells me or tells the software what are the source units of the STL geometry. So my units are meters, but some CAD can export inches or millimeters. So then you just need to switch to the source units of the STL. Number of components, usually for turbo machinery we can have stator, rotor, additional stators, and so on, multi-stage machines, and so on. So we can add more components to connect them and to, for example, set what is rotating and what is not. But we have now just one region, one component, which define the whole virtual tunnel geometry. Reference frame static, nothing is rotating, so the default is fine. We will be using the directory with STLs. So I will locate now the directory with my source STL file, so the source geometry. So I will go to TCAE here in tutorials, BIMBOL, and I will check this STL in which the input geometry is stored. Okay, then you can see that the name of STLs appear here. The ball is used for the CFD simulation, and BIMBOL solid is geometry for the solid for FSI analysis. So I will load this ball geometry. So we'll assign a type of the boundary in CFD world. So there is most general type, which is wall, so rigid wall, which somehow describes the rigid wall of any geometry. So I will apply it. Then we can see that this ball will appear in the render view. So now I need to create better dimensions of the virtual tunnel with respect to my beam ball, or with my ball without the beam, because now we are setting for CFD simulation. So the forces or the pressure will be the result of the CFD simulation, and these results will be taken to map on the FA mesh, and this will be basically the FSI connection, and then we will do the finite element analysis on another mesh, of course. So the bounding box. So let me set the proper dimensions. So I'm not sure now what is the topology. So let me load also the FA input geometry. So I will do here. Okay, STL file is solid. Okay, I will click apply. So now I see also the solid geometry. So I know that the flow goes in the Y direction. Okay, so I will adjust the virtual tunnel with respect to the setup of the input geometry. So go back and let me set. So X is the width of the virtual tunnel. So we can say 8 meters in a width. So the dimension should be large enough, because we would like to get rid of the boundary effects of the domain. So we should set it large enough. The Y is the length. So let me, for example, 5 meters before the ball and 15 meters, let's say, behind, because there is the wake area. So we we have to set it large enough, and the same with the height of the virtual tunnel. So I will set it in the same way like the width. So this, let's say this will be our virtual tunnel, and the direction of the flow is in the y direction. So we can set it here. So plus y, and this is our virtual tunnel setup or topology. Anytime during the setup phase, when you are setting the parameters, it's sometimes good to save the current setup, because if any time happen, or if you do something wrong, you can anytime reload your save state. So I would like to save it now, for example, to be sure that I do not lost anything if something happens. Okay, now about the mesh parameters. Okay, so this is the input, let's say input topology and input data, and now I need to set up the mesh. So the meshing tool is the SnapX mesh. So for those who are familiar with this tool, you know how it works. So it always works with so-called background mesh, which is consists of the hexahedras of the fixed size, and the size is set here in this background mesh size. So we would like to set something, let's say, large enough, because we don't care of the cell size apart from our object. So let's say I think the diameter is 30 centimeters. So let me set the background mesh size of, I don't know, 20 centimeters. So this will be the largest cell in the domain. So you can imagine that everywhere in the virtual tunnel there is the mesh which has all hexahedras, basically boxes of the size 20 centimeters. Okay, then you have to also define, because you have two options. You can mesh the ball from inside or from outside. So we would like to, of course, to mesh it from outside. So for this purpose, we have to set the internal point, which will define the domain, which will be meshed. This is just a helpful diameter of this virtual sphere, just to better follow the point. So I will increase it. So the default value is inside, but we would like to have it outside. So any point outside the ball and inside the virtual tunnel is okay. So I will use this one. This is okay. And now we would like to mesh the ball, of course. So, and we would like to have the mesh finer among the ball and coarse apart from the ball. So one of the parameter which defines the refinement of the mesh at the ball, or at the object here in the table, is these two columns. So let's say I don't want to have very fine mesh, because I would like to run everything runtime, and I don't want to wait for the results dozens of minutes. So I will do the mesh pretty rough, just for this training purposes. So I will use level 4. It means the cells near the ball will be refined 4 times, and refinement means that every cell will be splitted 4 times. So one splitting creates how many? 8 new boxes, right? So this will be done 4 times. Okay, and for example, just to imagine how the mesh will look like in this position, we can try to generate the mesh and see what we have set. So let me go back. If you go to the first item in the pipeline, I will save, and now we can run the meshing. Yeah, so here is we can call it manager. So first of all, if you change something and would like to run something, you need to write the case, which creates a case with the default name, or you can create your own name of the directory in which everything is stored, and then we can mesh. So because only the CFD component or CFD part is preset, so I will click on build to create the CFD part, CFD mesh. But what I have missed is important parameter, which is how many processor will be used, because everything is parallelized, or everything connected to CFD is parallelized. So to speed up speed up the meshing process, I can set the number of processors. So my computer has 10 processors, so I will set 10 processors. So let me abort the meshing, speed it up. Now if I run it, it will tell me that I have something changed. Yeah, I have changed the processors number, which you can see here, from 1 to 10, but I didn't click the write case. So I need to first click the write case to write a new parameter, 10 processors, and now I can click build the mesh, and now it is running in parallel on 10 processors. So can right, but maybe okay, I see I made another mistake, because just imagine the size dimension of the virtual box, and I thought I told 20 centimeters and not 2 centimeters, so the mesh will be extremely large. So you can see it was my first misprint, so this will be much finer. Sorry, coarser, but finer for the meshing speed. So again, write and build the mesh. Yeah, so now you can see the log. This is basically the output log of the TCAE software, or you can go also for the output of the SnapEx Mesh tool. So some of you, if you know the SnapEx Mesh and OpenFOAM, so you can see, okay, see the output log from the SnapEx Mesh. Whenever the meshing is ready, we can click show button. Here are the items which are visualizing each component. So I would like to now visualize just the CFD mesh. So I can click this item, CFD mesh. I can choose, for example, surface with edges, and to see what is happening inside, I can, for example, make a slice here, slice button, slice. The normal will be the, let's say, the X, yes. So, and in the middle, I think is the default. Perfect. And this is my, sorry, surface with edges. So this is my current setup. Okay, so let's say, okay, I'm satisfied with the refinement on the ball, but I'm not satisfied with the refinement near behind the ball and among the ball. So I can go back to the T-mesh and play with it. Okay, so what I had noticed now that some default, because maybe I check off the turbo machinery after the adding the box, so the default frame is rotating. So I will just switch everything to static, yeah, because there is no rotating component, of course. And for example, what I can do, the type, because I can simulate a virtual tunnel like it's built from the rigid walls, but I would like to simulate that the ball is levitating in the air, right? So I don't want to model the walls of the virtual tunnel like the rigid walls. So I can switch, for example, usually for symmetry, yeah, which is some geometrical property, like there was a symmetry, like if you copy the virtual tunnel everywhere. So this will mimic this symmetry type. Okay, and I would like to refine the mesh along the ball. So I can do it very simple. So I can enable the advanced properties, which are here. And if I click it, the new options will appear here. And here is the add refinement regions. So let me, for example, what we usually like, some refinement among the ball and refinement in the wake area behind the ball. So there are some implicit regions which we can use for this meshing, volumetric meshing. So let's say I will use some cylinders behind the ball. So I will click, for example, cylinder, the region 1, and let's say there will be some rough refinement in the wake area. So let me set the cylinder in the Y. Yeah, the Y direction is Y. So the first point is 0, 0, 0. So because the ball is placed in the origin, and so I will, for example, make 5-meter long cylinder with the radius which is a little bit higher than the radius of the ball, which is 30 centimeters, I think. So I will go for example, for 0.5. Okay, mode inside and level, let's say level 0 is this. So I would like to have 2 times refined mesh in the wake area in the big cylinder. Then I can create, for example, another region, again with the cylindrical shape, but a little bit shorter, let's say 2 meters, with the radius, like let's say a little bit lower than the previous one, and even higher level of refinement. And the last region, what I can do, for example, could be a sphere, which will be among the ball, to refine also in front of the ball, and with the radius, let's say also 0.4 to 0.4 to be smoothly connected to the cylindrical shape, for example, inside and level 3. Okay, and maybe the last thing, because for the external aerodynamics and for general CFD application, the boundary layers are important to properly model the boundary layer. So for example, I will add 5 layers at the ball, and here in the advanced meshing option in the layer mesh parameters, I would like to enable adding the layers, and here are some parameters. First, final layer. So final layer thickness would be, I don't know, I have 5 layers, so let's say 0.4, which is the parameter, which is the size relative to the cell size near the wall. Yeah, so it is a relative size. Okay, so let me check what we have set. So we can quickly remesh the mesh using the updated setup. So we added refinement regions, and we also added the boundary layers. So just to see if we have a proper mesh for the TCFD analysis. So usually this is standard work. You iterate to get the desired mesh, and when you are satisfied, then you can move to set up the TCFD simulation itself. So I think we are almost at the end. Yeah, now mesh is almost ready, and yeah, so I can click show the mesh. Perfect, and we can see that we have nice refinement among the ball and behind the ball, some gradually refined from the finer mesh to the coarser mesh to the coarsest mesh. So this could be a typical mesh for external aerodynamics, and we have also 5 layers here, which looks very nice. Okay, so this could be our CFD mesh. So now the second part is the mesh for the finite element analysis. It's much easier because it includes just few parameters. So let me go for the T mesh and for the FEI part. Okay, so STL is already loaded. So this is the input STL. Okay, let me get rid of it and okay, I will get rid of this point. Maybe show internal point as a sphere, and I would like to see FA geometry, not FA mesh. So this is our input geometry, and here are just few parameters for the netgen generator, mesh generator. So this is the sizing of the tetrahedras, maximum and minimum. I think the thickness of the beam is something like 1 centimeter, I guess. So I will set just some rough mesh again for a quick simulation. So let's say 4 millimeters is the maximum size, and let's say 2 millimeters is the minimum size. An important parameter is the optimization step for 2D and 3D steps of the meshing of the NetGen. So usually higher number generates higher quality of the mesh. So let's say 15 for 2D for the surface meshing, and then for the 3D meshing we will use higher number of steps. So something like this could be fine. Okay, so this as you have just seen, it's much more easier to preset the FAA mesh parameters. And let me try to generate the mesh quickly. Okay, so let's go for FEA mesh. So I think it will take some maybe 1 or 2 minutes. So, or maybe we can wait. We can wait for it. So again, there's some output of the NetGen generator. So now the surface mesh is already done. So there is 2 steps. First is NetGen generate first the 2D surface mesh, the triangles, and from these triangles goes inside to create the tetrahedral mesh. What we haven't mentioned that CFD, the tool which are used to solve the CFD simulation, is finite volume method, but for the FA analysis, the finite element method is used. Yeah, so these 2 methods are used: finite volume for the CFD and finite element for the FEA. Okay, so I think it's already, yeah, it's almost done. So volume is meshed successfully. Then some optimization steps are done by the NetGen to optimize the cell parameters, the tetrahedral parameters. And I think in few seconds we will see the resulting mesh. Yeah, it's almost done. Some quality parameters, yeah, and the finite element mesh is ready. So I can click show and visualize the FA mesh. So this is the resulting FA mesh. So you can see, you can check it here. Okay, so we can move to the TCFD and FA analysis setup. So let me save it, and now I can enable the modules for the CFD and FA simulation. So let me enable both of them. So new window appears here, which is used then for the runtime visualization of the results or of the intermediate results during the simulation. And two new items appears in the pipeline browser: TCFD for CFD setup and TFEA for FEA setup. So let's start with the TCFD. So there are several menus, so I will be just going through those which we need to change for this particular application. Maybe I will go to the standard setup. I don't need the advanced mode, which is here. So simulation type is not fun, is a virtual tunnel. Yeah, because the simulation is always focused. So based on the type, it will show you the important parameters and important post-processing features. Let's go for the physics. Here you can set if you would like to use the steady state or transient simulation. Speed lines are for turbo machinery, for compressors, for example. Speed line points, you can define as many points as you want to generate different scenarios, different physical conditions or boundary conditions for your simulation. But here we need just 1 point simulate at a given speed. So we just need 1 point, and let's say I will say 1000 iteration. It always depends on the application, on the mesh size, and so on. So there is no rule of thumb how many iterations are needed, because it depends on the problem itself. Fluid properties, we will go for incompressible mode. We will be using air, the default air, which is the air parameters at 20 degrees Celsius, I guess. We don't need any multiphysics. We will use K omega SST as a turbulence model, and we don't need any rotation reference frame because we are simulating the external flow without any rotation. Then in the simulation, in the solver, processors, again, usually you can use as many processors as you have, the physical cores you have on your PC. Numerical order, usually when you start or when you are setting up the case from very beginning, so I will always recommend to use first order, and if the simulation runs well, then you can switch to the second order. So let's say I will go for the second because I have already set up this case, so I hope everything will be fine. Although I am not sure if I do any mistake. Convergence tolerance is some parameter when to stop the simulation before the maximum iterations are reached. So this is just 0.1% of the oscillation of some quantities. An averaging window, which is the window of size of 100 iteration, or maybe I will set 200, over which the solution is averaged. Yeah, so because even we have steady state solution, steady state simulation, the results, pressure, velocities, and so can oscillate periodically. So we would like to smooth out this oscillation to get really the steady state result, constant result at the end. The controls are advanced parameter for the numerical solvers. Everything is set up per application, per solver, per physics. So you don't need to change them because they are set to default and robust values. Boundary conditions are important because here we define the conditions of the simulation. There are many boundary conditions, but we would like to now prescribe the speed of the flow, yeah, for the external aerodynamics. So I will choose just the, where is it, velocity, fixed velocity, yeah, here, and the direction. So the direction goes in the y-axis, following the y-axis, and I think the benchmark case was at 30 meters per second. The turbulent quantity, I can use some advanced turbulence parameters. So let's say turbulence intensity and turbulent length scale. So let's say I will use 1% of turbulent intensity, and length scale could be something like, I don't know, 10% of the diameter of our object. So which is, let's say, 3 centimeters, and the reference velocity is 30 meters per second, of course. Okay, I will maybe save my current setup for now to be sure that I don't lost everything. And let's continue. So this was the inlet boundary condition. Outlet boundary condition, just fixed pressure, zero, because we have incompressible case. So 0 can be applied, which is some kind of kinematic pressure, and we can understand it as a relative pressure where the atmospheric pressure is known, for example. The walls, we have just one wall, the ball, and we will use no slip boundary condition, which mimics the rigid walls with the friction. And standard wall functions, we can also use low Reynolds, but our mesh is not so fine that we can use low Reynolds wall function. It depends on the Y plus for those you know what I'm talking about. So based on Y plus, you can switch from standard wall function to the low Reynolds wall functions. And initial conditions, I can use, for example, the inlet turbulent values to get rid of the turbulence initial values. The pressure is 0, and velocity, I will help the solver because I know that the flow goes at 30 meters per second. So the initial condition will be 30 meters per second everywhere in the domain. And the last part is the post-processing. So there is the report from which places will be pressure drops and other quantity generated. This is mainly useful for turbomachinery cases, but for now I am interested, for example, just to see the force and some drag and lift coefficients, for example. This I can define here in the forces section. So let me enable it. Here I will define which patch to be used, or on which patch the forces will be evaluated. So the ball, the lift, okay, lift is Z, which is okay. The drag is Y, so I will switch to drag is Y. The pitch axis, I don't care, and torque axis, I think I don't care about that, about these two parameters. The reference area is, okay, is the reference area of the ball. So let me quickly calculate it. So it's P times, and the radius is 0.15 and squared. Okay, so this is, yeah, this is my, let's say this is my reference area. Okay, reference length is the diameter, let's say, and reference velocity is 30 meters per second. Okay, so let me stick with this setup. So I think I have set everything. We will see during the simulation if I set everything in the right way. Let's go for the save, and the last quick setup for the FSI analysis. So let me show you what can be done here. So we would like to map the results from the CFD to the FEA analysis. So it's under this fluid structure interaction checkbox. So the source is TCFD results. The patches which I would like to map is the ball, of course. I don't want to rotate. The ball because I have no rotation included in CFD simulation. I would like to map the forces from the pressure, so it will automatically compute the forces from the pressure and map them on the FIA mesh. And use relative pressure for computing forces. You can use both relative pressure compared to the ambient or the absolute. For some application, it is important, for example, to use the relative pressure because you have, for example, not the whole object within your simulation. So I will use, usually this is the safest option is the relative pressure, because you would like to have just for the deformation in this way of the displacement of the stick or of the beam. We would like to have we care just about the resulting force, not the absolute forces, right? Like if you use absolute forces, you expect, or you expect the, I don't know what, the vacuum inside, right? So we do not expect that inside the ball there is a vacuum condition. We don't need to care about the model analysis, which is usually for, let's say, for rotating machines or any other application, but I don't want to do the model analysis. For the solver, I will use the direct linear solver and the second order scheme, no, not scheme, the second order element in the FAI language, of course. And we can also apply the nonlinear equation, because if it's unchecked, it is used so-called linearized equations, which are much simpler, and the simulation is then quicker. And then nonlinear equations should be applied for larger deformation, for example. But for small deformation, the linear version can be used. So I will stick with this. Material properties, I will be using the default steel property or steel parameters, isotropic, the same in all direction, with this Young modulus, Poisson ratio, and material density. And the last thing we have to define is the kind of boundary condition. So we have to define which part we will be stuck in the ground, or which part will be fixed. So no deformation will be done. So we can define, we can fix this region to define it, to define the condition of the simulation. And this can be done by the region. So we can use the box in 3D, and just to read the position of the bottom of the beam is, we are in the Z direction, so -1 meter is the bottom of the beam. So let me define some rectangle, so minimum some high values, the maximum will be some high positive values, but for the Z direction I would like to stick somewhere here. So let's say 5 millimeters, 5 millimeter behind, above the lowest part of the beam. You can define if you would like to fix only the surface points or all the points within the volume defined by this box. So I think I can stick with this. Okay, so finger crossed. You can use the check setup if everything is set up properly, if something is not missing. So if you click it, okay, the first positive message here, case setup is okay. So now I need to write the case to write all my changes. Okay, perfect. Now I need to just, because I have something changed and the CFD mesh, just the some final operation has to be redone, not the whole meshing, but basically all these boxes must be in green. So I will just click the merge, which are some small modification of the mesh, and now we can go for the TCFD and FAA simulation. You can run everything from the very beginning, but everything will be run automatically in an automatically. So all the steps will be done without any interaction. So now because I have already mesh generated, so I will go step by step. So now I will run the CFD simulation. So you can anytime you can follow. Let's say I will enlarge these windows. So here are, for example, the quantity monitors and the residual monitors of the simulation. In the quantity monitors, you can anytime to switch to any quantities. So if you click on the CFD quantity monitor in TCFD, there is an item quantities. And if you click on the display bar here, you can choose any quantity which is evaluated. So let me check. Let me go for lift and drag coefficients, for example. There is always the instant value and the average minus average value, which is average over the last our window, which was 200 iterations. You can anytime zoom out or zoom in, or I like this approach. So if you click view and you will click the left axis custom range, so the CD are small values. So let me change the range from minus 0.1 to 0.5. Now you can nicely follow the CD and CL quantity. Okay, but you can, yeah, I would like to reset it to automatically appear, so to be automatically adjusted. So again, okay, this is the best. All right, so the CFD simulation is running. You can follow the quantities. You can follow some guess of the simulation. So the time left, which is 2 minutes now. So just to speed up the process, let's see. Just imagine that, okay, we see constant values of the average quantity. So CL and CD are almost constant. So I can skip to the next point. So I'm just saying, okay, for me the simulation is converged, and I can go for the next step. And now I can run, for example, FA analysis. So I can run FA simulation now because the results are available for mapping for FSI. And meanwhile, I can, for example, generate the full report, which are some automated generated report in HTML format to see the results of the CFD part of the TCFD module. So now it is generating, and at the end here in the HTML view we will see the report. And meanwhile the FA analysis is calculating. So for now, yeah, it was correct. So here we have the results of the CFD simulation. So these are the residual, some statistics of the mesh, of the simulation time, and other parameters. Here we can read the force coefficients, the convergence process. As you can see, this straight line shows me that here I click the skip point. So here basically is the end of the simulation where I clicked, and you can follow all the parameters which are interesting for you. at one place. So this is the report view. You can anytime visualize the results. So I can here click the show results. So let me get rid of the input or this FEA mesh. And now I can click show the CFD results. Yeah, so this is the domain. Maybe again, I can make a slice in the middle. And I can, for example, visualize the velocity contour. So this is the result of the CFD simulation and the pressure of the surface, which I can visualize here. So this item holds the data, and I can visualize just the ball and get rid of the slice, zoom, and yeah, this is the pressure distribution on the ball. Okay, and meanwhile, I think the FA analysis is also finished, so I can generate the FA analysis report and I can visualize the FA results. So let me apply it. Okay, so okay, there will be maybe a few seconds for the visualization of FA analysis. It is already done. So this is the FA results, and we can, for example, visualize the displacement of the ball. So we can, for example, read what is the displacement at this position. Here's a nice tool. You can pick any point interactively and read the coordinate displacement and other parameters, stresses in this particular point. There is also a nice tool using which you can visualize the deformation. Here's in the filters and alphabetical, here's the warp by vector. So I can click apply to really simulate, to really compare the displacement by the real, or you can magnitude it by some coefficient. Yeah, so this was the original position, and this is the, let's say, real position if the scale factor is 1. So this is the real position of the deformation. Yeah, and basically that's it. So we can, okay, for the final thing is to show you the report for the FAA analysis. So I can click here, visualize the report here, and this basically is the FAA simulation report. Again, some parameters about the mesh, how long the FAA analysis took, and static analysis, so the displacement, the larger displacement, minimum, maximum, and so on, and some stresses, and so you can then anytime you can follow this data because they are stored on the disk, and you can anytime visualize the results, both CFD and the FAA. Okay, so I think I've spoken for a long time, so I hope I have showed you the principles of working with TCAE, that you can see that within, for simple cases and smaller meshes, you can work immediately, interactively, and the work with TCAE is pretty simple and straightforward. So you just need to gain pretty small experience, and you can immediately work and play and do your own project with TCAE. Okay, so I hope Luboš is still there. Luboš, are you there?
Oh yes, Radek, thank you very much for an amazing
long, right?
yes presentation. No, it was great, and it was live, and you never know how it goes. So I especially value it was live. So thank you for it.
And I was pretty lucky that everything worked well without my human error. So
it's always difficult to set everything from scratch. So it's perfect.
Okay.
And I think we can go ahead. Yeah. So let's exactly. Let's make the Q&A now. There are a lot of questions already, so we are a little bit short of time. So we will pick a few most typical questions to answer, and then the rest will be answered later. So Radek, if you see one, pick one. Maybe I'll go.
Maybe I can take the first one. What is the meshing method used in TCAE? So as I already mentioned it, I think the SnapX mesh for TCFD or external meshes for TCFD, and for the finite element there is the NetGen software.
Yeah. Okay. The next question.
It was answered, I guess. Yeah, the finite element method is used for the FA analysis, and finite volume method is used for CFD analysis.
Yeah.
Right?
Specifically, right? There's Calculix inside for FEA, and there's OpenFOAM for CFD.
Yeah.
So
yeah, exactly.
the details are available. Maybe what we should definitely say, the details of this benchmark are available in the study, in the PDF on our website, and also on the website. So you can go there, take a look. You can download the case. You can play with your stuff. You can look at the results and give us your feedback. We'll be very happy to see.
Yes, exactly.
Yeah, so everything is online, so don't worry if you missed some details. You can still find everything, and the analytics, the analytical evaluation of the results on the website. So feel free to take a look, and you can always come back to us and ask, because for us it's a pleasure to answer all your questions. Okay, the next question: can we do probe check like in OpenFOAM? Yes, in the graphical interface of TCAE, you can do extensive post processing presets and see them later in the results. So probe is possible for sure. Yeah. So Radek, can you see some question you would like to answer right away? Or
I think that's all. I think we can answer the rest of them later on via email.
Okay.
And
okay. Some of them are specific, and some of them are very, very general. So it's difficult to answer very general questions. Yeah. So okay, we'll be back to all of you. So thank you for your questions. At the moment, we are a little bit short of time, so I think we can continue, which is basically it. This is gonna be it. Here are a few of those who already share our visions with us. So every one of you is welcome to join us along the way. We are like a family with our clients, so no one is ever left behind. So it will be our pleasure to welcome you in our family. And what next? I think this is gonna be it. Yeah. So I think it's time to thank you, Radek. Is there some last word you would say?
No. It was just amazing experience for me to show it live, and thank you all of you who came and watched this webinar, and we are looking for future cooperation with all of you.
Okay.
So thank you, and see you next time.
Okay. Okay. Thank you all. Thank you, Radek. I'll leave you all with that. Feel free to contact us. For us, it's a job, but also a pleasure. It's a pleasure for us to collaborate with you. So thank you, and bye bye. Sometime next time.